Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I do, making lecture and sample problem videos for your benefit, then please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and you can inspire and energize me to keep me going. So here is sample problem 3. A rectangular timber beam section 75 mm by 150 mm is carrying with a uniformly distributed load of 600 newtons per meter over its entire simple span of 3 meters. Neglecting the weight of beam, determine the bending stress and the horizontal shearing stress at 1 meter from left support and 25 mm below the top surface of the beam. So let's answer each part first to focus our attention. So for part A, let's draw the figure. We have a simply supported beam 3 meters long. So the reaction should be WL over 2, where W is equal to 600 newtons per meter or 0.6 kilonewton per meter. So therefore, at 1 meter from the left support, so we have the shear V1, let's call it V1, and the moment M1. So for moment M1, it is just cutting the section and take moment about section 1. So it is WL over 2. M1 is WL over 2 times 1 minus the moment of the load, which is W times 1 times zero point 0.5. Moment arm is 0.5 meter. So substitute the value of W, which is equal to 0.6 kilonewton per meter times length 3 over 2 times 1 minus 0.6 times 1 times zero point 0.5. So therefore, M1 is equal to 0.6 kilonewton meter. So bending stress formula. So let's draw the section. This is the section in particular 25 mm below the top surface. And therefore, if this is the neutral axis, the distance from the neutral axis to that section would be 50. In other words, y is 50 mm. So bending stress is my over I in general. Then at this section, we'll call that bending stress at section 1. And m is m1 and y is 50 mm. And moment of inertia is bh cube over 12. So sigma 1 is m1, which is 0.6 kilonewton meter times 1000 square to make it newton mm. Y is 50 mm divided by 75 times 150 cube over 12. So that would be in mm to the fourth. The units here would be newton per meter mm square or megapascals. So sigma 1 is 1.422 megapascals, and because the elastic curve will be smiley, the top fiber will be in compression, or because the moment is positive, the top fiber is in compression, the bottom fiber tension, but this section is above the neutral axis, so it is in the top fibers, therefore it is in compression. For part B, the maximum bending stress and its location. So the maximum bending stress occurs where moment is maximum, and that is at the center. In particular, it occurs at the top and bottom fibers of the section. So for shear 1, first, we have not yet finished part A. So shear at this section is equal to WL over 2 minus W times 1. It's like summation versus Y. So WL over 2 minus W times 1, where W is 600 Newton per meter to express V1 in newtons. So 600 times 3 over 2 minus 600 times 1. So shear at section 1 is equal to 300 newtons. Then the formula for shear at for shear stress in general is VQ over IB. Then V is 300. Q is the static moment of area above this section, above this. So this is the area, 75 by 25, and the distance of each centroid from the neutral axis is half of 25, 12.5 plus 50, so 62.5. So Q is area, which is 75 times 25, and moment of that area or distance of the centroid of that area to the neutral axis, 62.5, and B is 75 mm, the width of this line. So V is 300, area is 75 by 25, moment arm 62.5 from the neutral axis, or distance of centroid of the area above this section to the neutral axis is 62.5. Moment of inertia of section 75 h cubed over 12. Then B is also 75, the length of that line. So solving for shear stress at section 1, 0.0222 megapascals. Newton, everything, the units are Newton and mm, so therefore the result would be in megapascals. So let's convert that to kilopascals by multiplying 1000. So shear stress at section 1 is 22.22 kilopascals. Then for part B, the maximum bending stress and its location, it is expected it occurs at the center of the beam, where the maximum moment is WL square over 8. And for the section of the beam, it occurs at the top or bottom fibers. So sigma max equals 6m over BH square for rectangular section. So equate sigma max with its allowable, we're computing for sigma max. M is WL square over 8. So 0.6 times 3 square over 8 to express it in kilonewton meter. So 0.675 kilonewton meter. So substitute. Let's express kilonewton meter to Newton mm by multiplying 1000 square. So 6 times 0.675 1000 square over 75 150 square. So the units would be in megapascals, and it is equal to 2.4 megapascals, either compression or tension. Compression at the top, tension at the bottom, and that occurs at the top and bottom fibers. And in particular, the location is at the center of the beam. And letter C, the maximum shearing stress and its location. The maximum shearing stress occurs at the neutral axis of the section, and the maximum shear occurs either just to the right or just to the left of the support, simple support. So for letter C, tau max equals 3V over 2A, if you can remember, for rectangular sections. Then maximum shear is WL over 2, which is 600 Newton per meter times 3 over 2, and that is 900 newtons. So V in newtons, area in mm square, so that would be in megapascals. So tau max equals 3 times 900 over 2 times 75 by 150. So in megapascals, maximum shear stress is equal to 0.12 megapascals. So our answer is tau max equals 120 kilopascals. And that happens at the neutral axis of the section, and its location is either just to the left or just to the right of the support. At neutral axis, then just to the left or right of support. Then let's proceed to letter D. So for letter D, the maximum safe uniformly distributed load it can carry if the beam, if bending stress controls and the allowable bending stress is 8 megapascals. So let's use the formula. Maximum bending stress equals 6m over BH square for rectangular section. So allowable bending stress is 8. So 8 equals 6 times m, assuming m in kilonewton meter. So we multiply 1000 square to convert that to Newton mm over 75 150 square. So m in kilonewton meter is, m max in kilonewton meter is 2.25 kilonewton meter. And we equate that to WL square over 8. So 2.25 equals W 3 square over 8. So the maximum safe uniform distributed load if bending stress controls in kilonewton per meter is equal to 2 kilonewtons per meter. Then letter E, the maximum safe uniform load if shear stress controls and the allowable shear stress is 600 kilopascals. So again, we use tau max equals 3V over 2A for rectangular section like this one. So tau max or tau allowable is 0.6 megapascals equals 3 times maximum shear. Assuming maximum shear in kilonewtons, so that we multiply 1000 to convert that to newtons over 2 area 75 by 150. So shear in kilonewtons is equal to 4.5 kilonewtons, and we equate that to maximum shear, which is the reaction just to the left or just to the right, WL over 2. So 4.5 equals W times length 3 over 2. So the W is equal to 3 kilonewtons per meter if shear stress controls. Then letter F, the maximum uniform load that the beam can carry if the beam is oriented such that the 150 mm dimension is horizontal and the allowable stresses for shear and bending are the same as mentioned above. So for letter F, this is now the orientation of the cross-section. B is 150 and H is 75. So if bending stress controls, so still sigma max equals 6m over BH square, where this time B is 150 and H is 75. So 8 equals 6m, assuming m in kilonewton meter, so times 1000 square, over B, which is 150 this time, H is 75. So 150 75 square. M in kilonewton meter is equal to 1.125 kilonewton meter, and we equate that to WL square over 8, or W times 3 square over 8. So 1.125 equals W 3 square over 8. So W is equal to 1 kilonewton per meter. If shear stress controls, same formula. So we expect, because area is 150 by 75, which is the same as 75 by 150, we expect the same answer of 3 kilonewton per meter. So let's just repeat it here. So 0.6 equals 3V, assuming shear is 1 in kilonewtons. So times 1000 over 2 times 150 times 75. So shear max is 4.5 kilonewtons, and it is WL over 2 in general, which occurs either just to the right or just to the left of the support. So 4.5 equals W times 3 over 2. So W equals 3 kilonewton per meter. Since the lower value controls, so bending stress controls, so the safe uniform load the beam can carry in this orientation is equal to 1 kilonewton per meter. So that's it for this problem. I hope that you were able to follow. And this is just a basic problem.